Hello and welcome back. We are on Chapter 9 in Fundamentals of Inorganic Glasses, which is all about viscosity. We are going to cover the topic of viscosity over the course of the next 3 lectures. Today, in Lecture 18, we're going to cover what is viscosity, how does viscosity scale with temperature, and how do we measure viscosity. So, diving in, viscosity is a liquid state property. Liquids flow under the force of gravity or under other applied forces, and that resistance to flow is described by the viscosity. So, in that way, viscosity is the opposite of fluidity. Fluidity tells you how fast something flows. Viscosity tells you how slowly something flows. So, what is the resistance to flow? What this means is that the greater the value of the viscosity, the slower the flow. And this shows an example here from Corning, which shows pouring some molten glass out of a crucible, and the rate at which the molten glass flows out of the crucible is governed by the viscosity. The higher the value of the viscosity, the slower the flow. Viscosity is important because it governs every stage of glass manufacturing, from the melting of the glass at high temperatures through the forming operations. Every stage of glass manufacturing is governed by how fast the glass or the glass forming melt is flowing. And so viscosity is one of those most critical properties for glass manufacturing and also for the use of glass, because the viscosity of a glass governs how high you can take it up in temperature before it starts to flow. So what is viscosity? The rate of flow depends on the viscosity and the applied forces on a system. The viscosity coefficient is given by the Greek letter eta, and this relates the shear stress to the velocity of the deformation. So the coefficient of shear viscosity, eta, is equal to the shear stress divided by the shear strain rate. That ratio gives our coefficient of shear viscosity, which means that the greater the viscosity, the greater the applied stresses are required for a given rate of deformation. Now, the units of viscosity are Pascal seconds for SI units, and you might also see in the older literature viscosity expressed in units of poise. The conversion factor between Pascal seconds and poise is very simple. It's just a factor of 10 difference, where 1 Pascal second is equal to 10 poise. Now, if we write this out in terms of an equation here, the shear stress, we know it's a shear stress because it has two subscripts here, sigma xy. So this is a shear stress or a biaxial stress. And stresses have SI units of pascals. And then this is related to the shear deformation rate, or the shear strain rate. If the shear strain here is given by E sub xy, the shear strain rate is the time derivative of that. So that is indicated by a dot on top of the E. And this shear strain rate then has units of per second, so inverse seconds. Therefore, this constant of proportionality, which relates the shear stress to the shear strain rate, is it must have units of Pascal seconds. So this coefficient of shear viscosity, also known as simply the shear viscosity, or simply the viscosity, has units of Pascal seconds. Now, if someone just says viscosity without saying shear viscosity, they almost always mean shear viscosity. There is also a property called the bulk viscosity, which we will get to at the end of the lecture. That is rarely used because it is very difficult to measure, and so it is not reported very often in the literature. So if someone just says to you viscosity, most of the time, the vast majority of the time, what they mean is the shear viscosity, and specifically this coefficient of shear viscosity given by eta. The liquid viscosity is so important because the maximum use temperature of a glass or polymer product is given by its viscosity. And also all the temperatures that are required for glass or polymer manufacturing is governed by the viscosity curve of that particular system. So the viscosity temperature relationship determines design requirements and operating conditions for melting furnaces and for forming equipment, and also for any post-forming processes. Now, in the glass community, it is common to define several reference points for viscosities. These are the temperatures at which viscosities are at certain critical values. Now, if we look at this viscosity temperature relationship, this is kind of just an arbitrary one here, without any numbers on the temperature axis. But what you'll see is that the y-axis is not just the viscosity in linear units. In fact, it is the logarithm of viscosity. This is the base 10 logarithm of viscosity, where the viscosity is in units of Pascal seconds here. And so what we see is that as the glass forming melt cools from its melting regime down to its glass transition temperature and down below its strain point, the viscosity is increasing by many orders of magnitude. It's increasing by more than 12 orders of magnitude. So this is an enormous change in the shear viscosity of the melt as it is cooled down through the glass transition and into the glassy state. And this is part of what makes viscosity such an interesting property to study, is because it's changing by so many orders of magnitude. Now, it's common to define several viscosity reference points. Um, there are the melting point, the working point, the softening point, the glass transition temperature, and the strain point. And each one of these viscosity reference points is defined based on having a particular value of viscosity. This is also known as an isocom temperature. ISO meaning the same, and com, KOM, meaning viscosity. So these are temperatures of constant viscosity. If we start at the high temperature end, the melting point as a viscosity reference point is defined as being the temperature at which the viscosity is about 10 Pascal seconds. This corresponds to a typical temperature where glass is melted in industry. And I would like to point out that this melting point, defined as being where the liquid has a viscosity of 10 Pascal seconds, this is different from the thermodynamic melting point of a crystal. So this is actually completely unrelated to a thermodynamic melting point. The thermodynamic melting point is where the Gibbs free energy of the crystal is equal to the Gibbs free energy of the liquid. This melting point is based purely on the liquid itself, and it just corresponds to a typical viscosity at which glass melting operations are performed. So 10 Pascal seconds. Now, as the glass forming liquid is cooled below the melting point, so as the temperature goes down, the viscosity is increasing by orders of magnitude. And the next reference point that we define is called the working point. The working point is the temperature at which the viscosity is 10 to the 3 Pascal seconds. So this is the viscosity at which a machine is able to work on the glass forming melt without losing control. Now, below the working point, if we continue to cool the system below the working point, the viscosity continues to increase by orders of magnitude. And the next reference point that we define is the softening point. The softening point is the temperature at which the viscosity is 10 to the 6.6 Pascal seconds. And this is the approximate viscosity at which a glass or polymer will deform under its own weight on the time scale of a manufacturing process. So most of the glass forming operations that take the molten glass and get it into the shape that you want to make, most of those processes take place in what's called the working range. The working range is all of those temperatures between the working point and the softening point. The working point is where you can start to work on the molten glass and put it into a shape in a controlled manner. And the softening point is basically the temperature below which the glass is not going to deform under its own weight on the time scale of the manufacturing process. So in between those two reference points, in between the working point and the softening point, that's where most of the glass forming operations take place. Now, if we continue to cool below the softening point, the next viscosity reference point is at 10 to the 12 Pascal seconds. And this has two different names that in this, for the purposes of this discussion, both mean the same thing. And those are the glass transition temperature or the annealing point. And from the point of view of viscosity, they both indicate the temperature at which the viscosity is 10 to the 12 Pascal seconds. It's sometimes called the annealing point because this is the temperature at which glasses are often annealed after forming because stresses in the glass get relieved in a matter of minutes if you hold the glass object at the annealing point. For example, if a glass artist blows some glass object and that needs to be put into a furnace to help alleviate the stresses that developed upon cooling, usually that would be done at the annealing point. Um, it's also called the glass transition temperature because the same viscosity of 10 to the 12 Pascal seconds is where we typically get a falling out of equilibrium and where we undergo the glass transition to convert from a liquid state to a glassy state. And on a typical laboratory timescale, that occurs around a viscosity of 10 to the 12 Pascal seconds. So either one of these, annealing point or glass transition temperature, in the context of viscosity, refer to the same viscosity isochrome of 10 to the 12 Pascal seconds. Then if we continue to cool below the glass transition temperature, the highest viscosity and last viscosity reference point that gets defined is the strain point. The strain point is the temperature at which the viscosity is 10 to the 13.5 Pascal seconds. At this point, at the strain point, stresses that form in the glass object are relieved in a matter of hours as opposed to a matter of minutes at the annealing point. And the strain point is also useful because this corresponds to a rough estimate of an upper use temperature of a glass product. So if you were to take your glass, heat it up to the strain point, you can hold it there for a short period of time without it deforming. However, if you hold it there for too long, it will, of course, start to deform. Now, a few things to note about these viscosity reference temperatures. First of all, they are purely arbitrary and they are defined based on glass industry considerations. So unlike thermodynamically determined transition temperatures, such as the thermodynamic melting point or boiling point, these viscosity reference points here are somewhat arbitrarily defined. They are just defined based on industrial convention. For example, it is perfectly possible to anneal glass over a range of temperatures, either a little bit higher or a little bit lower than the annealing point, and that is perfectly fine. It doesn't have to be done at the exact annealing point. Now, what are some of the typical process viscosities that are used in industry? This is a table that comes from George Hares, who was a very well-respected scientist at Corning from many years ago. And this is an older table, so the viscosities are given in units of poise instead of Pascal seconds. If you want to convert this from poise to Pascal seconds, you just divide all of these numbers by 10. Now, at the melting side of the glass tank, the melting is typically done at a viscosity of 100 to 500 poise. This means 10 to 50 Pascal seconds. This, of course, corresponds to the melting point that we just discussed, which had a viscosity of 10 Pascal seconds. Moving on to the working end of the glass tank, typical viscosities are on the order of 200 to 1,000 poise, so about 20 to 100 Pascal seconds. Pressing operations take place at 1 to 7,000 poise. The ribbon machine, which we'll get to a bit later in this course, and was used for making glass light bulb envelopes, this operates at about 3,000 to 10,000 poise. Glass tubing is made at a somewhat higher viscosity of 20,000 to 100,000 poise, and the Corning Glassworks sheet drawing process takes place at even higher viscosities, from 100,000 to a million poise. So you can see that the specific viscosities that are relevant for particular glass forming operations depend on how that forming equipment is designed, and it depends on the type of shape that you want to make. We're going to be getting into all of these once we get to chapter 22 in the book, which is about glass industrial processes. Here's another older plot. This shows viscosity versus temperature for a number of industrial glass compositions from Corning. And what we can see is that different glass compositions can have dramatically different temperature dependencies of viscosity. So the plot here shows the base 10 logarithm of viscosity in poise. So this is going from 10 to the 4 poise all the way up to about 10 to the 16 poise. And this is as a function of temperature in degrees C. And what we see here is this is the annealing point, which is at 10 to the 13 poise, or 10 to the 12 Pascal seconds. The strain point is at 10 to the 14.5 poise, which is 10 to the 13.5 Pascal seconds. And where these different viscosity curves cross those points, that cross those lines, that's how we identify where the annealing point is and the strain point for those different compositions. So for example, for fused silica, which is pure SaO2, this has a very high strain point, which if you pull this down to the temperature axis, is close to about 1100 degrees C. It has an annealing point that's closer to 1200 degrees C. And this is one of the highest viscosity curves of any glass forming system. And if we take fused silica and add other components to it, like modifiers, this tends to lower the viscosity at the same temperature. So for example, if we go from fused silica to any of these other glasses, such as 0080, which is shown here highlighted in blue, this is a soda-lime silicate glass. You see that this viscosity curve is dramatically lower than the fused silica viscosity curve. And that's because of the incorporation of network modifiers like sodium oxide and calcium oxide. They convert bridging oxygens in the fused silica to non-bridging oxygens. That lower conductivity of the glass network is what lowers the viscosity. Now, somewhat in between soda lime and fused silica is the 1720 glass. This is an aluminosilicate composition, and you see that the viscosity curve falls somewhere in between. But note that the viscosity is changing by many orders of magnitude here with composition, and it's also changing by many orders of magnitude with respect to temperature. And so over the course of the next 3 lectures, we're going to deal with both the temperature dependence of viscosity as well as the composition dependence of viscosity. Now, if we want to learn more about viscosity, we need to know how to measure it. And because the viscosity is varying by so many orders of magnitude, there's not just one measurement technique that can be used to measure that entire viscosity curve. There are, in fact, many different measurement techniques for mapping out the entire viscosity curve. At the high temperature end, say in the melting regime, at lower values of viscosity, 2 of the methods that are used are the Stokes either falling sphere or bubble rise method, and then the Margoul's rotating cylinder method. The Stokes method is based on Stokes' law, and there are 2 ways to implement this. One would be to have a column of the molten glass at constant temperature, and if you're doing a falling sphere approach, you take maybe a stainless steel ball, some ball that has a higher density compared to the glass, drop it at the top of the column of the molten glass, and then measure how long that it takes to sink to the bottom of the column. And that the amount of time that it takes depends on the density difference between the ball and the molten glass. And it also depends on the radius of the ball and the viscosity of the liquid. So if you know the densities and you know the size of the ball, then you can calculate the viscosity of the liquid based on how much time that it takes for it to fall to the top. Another variation on that is the bubble rise method, where instead of dropping a ball from the top, you would inject some gas from the bottom of the column. That would form a bubble, and then the bubble would rise to the top. And again, based on the density difference between the bubble and the melt, and the size of the bubble and the time that it takes to rise to the top, that gives you the viscosity of the liquid. Now, that can be used, but the problem is that it only gives you one value of viscosity at that particular temperature. A better approach is the Margoul's rotating cylinder method, and so I'll give you some more details on that on the next slide. But this is able to measure viscosity over a range of several orders of magnitude. And so you can get kind of a big chunk of the viscosity curve with a single measurement using that approach. Now, if we cool the system down and get to lower temperatures or higher viscosities, we have to use a different set of techniques. One of the ones that we will cover on one of the later slides is the parallel plate method, which can be used over viscosities between about 10 to the 5 and 10 to the 9 Pascal seconds. Another approach is penetration viscometry, which isn't quite as accurate. There's also fiber elongation and beam bending, which we will cover in detail. And then another method, which isn't quite as accurate, is this disappearance of stress method. And we're not going to cover that one in class because it's not used too much. The ones that we're going to cover in more detail are the rotating cylinder method, parallel plate, fiber elongation, and beam bending, because those are the most useful methods for getting accurate values of viscosity. So let's start with this Margoul's rotating cylinder method, also known as rotational viscometry. You can see a picture of the setup over here on the right. Basically, the viscometer consists of a furnace, and that furnace is going to undergo some specified temperature path. Within the furnace, there is a crucible, and in that crucible, we place the glass to be melted. Usually, this crucible is made out of platinum or some platinum rhodium alloy, so it can achieve the high temperatures required without interacting with the molten glass. So the glass powder or glass cullet is put into the crucible and is put into the furnace and then heated up to a high temperature where it melts. After it has melted, there's a spindle at the end of the cylinder here that gets submerged into that molten glass. And this is fixed to a motor, and the motor is going to rotate the cylinder using either a fixed torque or by changing the torque to get a fixed rotational viscosity. But in either case, the amount of torque that it takes to get some speed of rotation relates to the viscosity of the melt at that particular temperature. So if you've got a higher viscosity melt, then it takes more torque in order to achieve the same level of rotational viscosity. If it's a more fluid system with a lower viscosity, then less torque is required in that case. And then what you can do is change the temperature of the furnace here. You may want to start at high temperatures where it's more fluid and then gradually lower the temperature down. As you lower the temperature down, the viscosity is increasing and it takes more torque to get the same rotational speed. This covers a pretty wide range of viscosities. Rotational viscometry can be used anywhere from 1 Pascal second up to about 10 to the 6 Pascal seconds, and in some case up to 10 to the 7 Pascal seconds. The normal design of this equipment is to have a fixed crucible and then rotate the spindle on the inside. There are alternative designs, including one where the spindle is fixed and the crucible is rotated, but it's fundamentally the same type of measurement. If we zoom in on the spindle, it typically has a shape like this. The spindle would be made out of platinum or platinum rhodium alloy, and the crucible is also made out of platinum or a platinum-rhodium alloy. Um, and the spindle is often attached to a smaller diameter shaft. Different geometries are possible, and one just has to account for the specific geometries and make sure that you've calibrated the equipment to ensure that you get good values of viscosity. Now, in the polymers community, everything is shifted down to much lower temperatures compared to the inorganic glass community. The same type of equipment is used, but it doesn't have to achieve nearly as high temperatures, and much less expensive materials can be used since they would not require the use of platinum or rhodium. Now, the next method that we'll cover is fiber elongation. Fiber elongation can give you quantitative results, but not quite as accurate as the other techniques that we're going to discuss. Basically, the fiber elongation method consists of suspending a glass fiber in a furnace. This furnace is set at a particular temperature. And the fiber will either elongate under its own weight in response to gravity, or if the temperatures are lower, you can also attach a weight to the end of the fiber to help it elongate. And then what we do is measure the rate of elongation of the fiber. A faster elongation rate indicates a greater fluidity of the fiber, which means a lower viscosity. This needs to be calibrated using known standards. The useful range could actually cover quite a wide range of viscosities. The downside is that it is kind of a less accurate method compared to other approaches. So I personally consider fiber elongation to be kind of a quick and dirty method to give you an estimate of viscosity, but I wouldn't recommend using this to give you very precise values. A better approach in this intermediate range of viscosities is the parallel plate approach. With a parallel plate viscometer, we have a disc-shaped sample that is placed in this kind of sandwich configuration between two parallel flat surfaces. So there's a pedestal here with a sample holder. You put this disc-shaped glass sample on top of it, and then a load rod comes down, and then there are two parallel surfaces then that basically sandwich the glass sample in between. One of the surfaces is fixed in position, and then the other is free to rotate. And again, there's a relationship between the torque that's applied to rotate versus the rotational velocity. And the greater amount of force that's required, the higher the viscosity. So it's kind of a twist on the rotational cylinder approach. The difference is that for parallel plate, the viscosity is high enough that you can't really submerge something into this higher viscosity sample. You're just kind of pressing up against it. The useful range for the parallel plate method is anywhere between 10 to the 5 and 10 to the 9 Pascal seconds. Oftentimes, parallel plate equipment is optimized to give measurements of the softening point, so 10 to the 6.6 Pascal seconds. And this would provide the most accurate and the most precise measurement of the softening point. Now, if we continue on to even lower temperatures, now the glass forming melt is approaching or even into the glass transition range. And so now it is approaching more of a solid-like behavior. And so with this solid-like behavior, we need to use more of a solid-like approach. So beam bending viscometry consists of making rectangular bars out of your glass sample and putting it in a three-point bending configuration, as shown here, where there are two supports on the left and the right. And then a load is applied in the center, either by pressing downward, like with a push rod on top, or by hanging a weight to it. But in any case, it is in a three-point bend configuration. And then we measure the rate of deflection here. So the rate of how quickly this glass beam is deflecting with respect to its initial planar configuration. A higher deflection rate indicates a lower value of viscosity. And this needs to be calibrated with known standards. And it can be used over a pretty wide range of viscosities. shown here is 10 to the 7 to 10 to the 16 Pascal seconds. It's more commonly used over the ranges of, say, 10 to the 10 through 10 to the 13 Pascal seconds. If you get to lower values of viscosity, it can be kind of hard to control. And if you get to higher values of viscosity, you just have to be more and more patient in order to observe the deflection process. But this can give you very accurate measurements of viscosity. It can also be used to measure the non-equilibrium viscosity of the glassy state to show how the viscosity evolves as the glass relaxes. So when we put all of these different measurement techniques together, you can get a pretty good sense of the entire viscosity curve. The next concept that I want to introduce is due to Austin Angell, who was a professor at Arizona State University. And one of his major contributions to science is the so-called Angell plot, where what he did was he took the viscosity versus temperature data for a wide range of different glass-forming chemistries. You can see silica on here, germania, chalcogenide systems like arsenic sulfide, modified silicate systems like sodium silicate. There's ionic liquids like zinc chloride, organic liquids like or O-terphenol, toluene, and so on. So very different chemistries. And he put them all on the same normalized plot. And the way that this plot is configured is that the y-axis has the base 10 logarithm of viscosity. You'll see that there's a left-hand y-axis and a right-hand y-axis. The only difference here is the units in which the viscosity is being expressed. On the left-hand axis, this is the log of viscosity in poise. On the right-hand side, it's the log of viscosity in Pascal seconds. Since it's a base 10 logarithm and there's a factor of 10 difference in going between poise and Pascal seconds, on a logarithmic axis, it's just a difference of 1. So, for example, 10 to the 13 poise is the glass transition temperature, and that corresponds to 10 to the 12 Pascal seconds. Now, the trick here is in the x-axis, and the way that Angell plotted this is using a normalized inverse temperature. So he plotted the inverse temperature, 1 over T, but that inverse temperature is normalized by 1 over the glass transition temperature. So it's 1 over T over 1 over Tg, which gives us Tg over T. And this goes from 0 all the way to 1. And this normalized inverse temperature of 1 is where the temperature is exactly equal to the glass transition temperature. Tg over T equals 1. So this is the glass transition temperature. And according to this definition of the glass transition temperature, all of these viscosity curves, regardless of chemistry, all pass through a common point of 10 to the 12 Pascal seconds. So they all pass through this common point of 12. And this is by definition, because by definition, the glass transition temperature for any liquid of any composition X is the temperature at which the shear viscosity is equal to 10 to the 12 Pascal seconds. So all of these curves all pass through this common point at Tg over T equals 1, because by definition, the glass transition temperature is where the viscosity of the liquid is equal to 10 to the 12 Pascal seconds. Now, if we go to the other side of the plot, here the Tg over T is equal to 0. And that does not mean 0 temperature. What it means is infinite temperature, because it's the inverse temperature equal to 0. So obviously we don't have any direct measurements here in the limit of infinite temperature. So all of these curves are extrapolated. And what Angell found is that if he extrapolated all these curves for all these different systems and extrapolated that to the limit of infinite temperature, that they all appeared to pass through a common point, which corresponds to 10 to the minus 4 poise, or 10 to the minus 5 Pascal seconds if we read off of the right-hand axis. And this kind of the hand-waving explanation of this is that in the limit of infinite temperature, there's an infinite amount of thermal energy, and so bonding doesn't matter anymore, and everything is able to flow in the same way, independent of chemistry, because the chemical bonds no longer matter. So it's kind of an empirical observation that everything passes through a common point in the limit of infinite temperature, and by definition, everything passes through a common point at the glass transition temperature. Now, what Angell noticed after making this plot is that he observed two different types of scaling behavior. A couple of systems, namely silica and germania, showed pretty close to a straight line scaling on this plot. So if we have a straight line on a log of some property versus inverse temperature, that straight line scaling indicates an Arrhenius behavior, or Arrhenius dependence of that property on temperature. And a couple of systems, silica and germania, do indeed show that type of Arrhenius scaling. However, most of the other systems, so basically everything else here, either the modified silicates, the chalcogenide systems, the ionic systems, the organic systems, they all showed some significant departure from Arrhenius scaling. And these non-Arrhenius viscosity curves therefore showed some degree of curvature. So what Angell did was he classified liquids into two categories, where the ones that showed this Arrhenius scaling are labeled as strong, and the ones that exhibit non-Arrhenius scaling are labeled as fragile. Now, this terminology is a little bit unfortunate because if you just say strong or fragile, you would think that that has something to do with the mechanical strength or the mechanical fragility. In reality, Angell is defining these as liquid state properties rather than solid state properties. So if a liquid is strong, what this means is that the activation barrier for viscous flow is not changing with temperature because the slope of these curves is the same independent of temperature if you have this straight line Arrhenius scaling. And so if the activation barrier is a constant, this indicates that the structure of those liquids is probably not varying by very much as a function of temperature, so that the structure of those liquids can be described as being strong. So that's what Angell means by saying strong liquids. On the other hand, for fragile liquids with high fragility, what we see here is that the slope of these curves is changing rather dramatically with temperature. You've got a much larger slope here in the low temperature regime near the glass transition, and a much lower slope in the high temperature regime. And so if we start at high temperatures, there is a low slope, therefore a small activation barrier. And then as you decrease the temperature, the slope is increasing by more and more and more until we get to the glass transition temperature here. And what Angell deduced from this curve then is that the change in the slope with respect to temperature indicates a change of the activation barrier. And what that indicates is that the structure of the liquid is undergoing some sort of dramatic change as a function of temperature. And therefore, the structure of the liquid he called fragile. So a fragile liquid is one that exhibits non-Arrhenius scaling of viscosity with temperature. A strong system is one that exhibits Arrhenius scaling of the viscosity with temperature. Now, Angell did one more thing. Actually, he did a lot more things, but one of the important things that he did was to quantify the degree of fragility by defining this fragility index, which is given by a lowercase m. And the fragility index is defined as being the slope of this curve at the glass transition temperature. So in other words, the slope of the base 10 logarithm of the shear viscosity with respect to this normalized inverse temperature, dTg over T, evaluated at the glass transition temperature, where T equals Tg. And what we see is that the strong liquids here, like silica and germania, have a lower slope at the glass transition temperature, whereas the more fragile systems have a steeper slope. Now, the interesting thing about this too is that fragility is a second derivative property because it is telling us something about the curvature of the viscosity versus temperature relationship. A low fragility, meaning a strong system, has zero curvature because it is a straight line. As you increase the fragility, it's increasing the curvature here. But the fragility index defined by Angell is not a second derivative property, it is a first derivative property. And the reason that we can get away with this is because of these common points. The common point of the glass transition temperature and the common point in the limit of infinite temperature, which means these 2 points at either side are fixed. And so if you were to increase the curvature, that increase in curvature must correspond to a shallower slope at the high temperature end and a correspondingly steeper slope as you approach the glass transition temperature. And so what this means is that we can take this first derivative property of the fragility index and use that to tell us how much curvature that the viscosity versus temperature relationship will have. So this fragility index here is telling us how steep the slope is, but that's also telling us how great of a departure from Arrhenius scaling we have. So this Angell plot is important because it classifies liquids as either being strong or being fragile. It also shows us the common intersection points at the glass transition temperature because of the definition of the glass transition temperature as an isocom temperature where the viscosity is 10 to the 12 Pascal seconds, and the second convergence point in the limit of infinite temperature. And therefore the definition of fragility index here as the slope of this line at the glass transition temperature itself. So we're going to keep coming back to the Angell plot in our discussion of viscosity because it is conceptually quite important. And we're going to come back to that in the next lecture that deals with models of the viscosity-temperature relationship. But at the end of this lecture, I just want to point out a few special cases of viscosity. Everything we have discussed up to this point has considered Newtonian viscosity, which is a linear relationship between the applied shear stress and the shear strain rate in response to that shear stress. What this means is that for a Newtonian fluid, there is a single value of viscosity that is independent of the shear rate. And that is what is shown here on this lower plot, that the viscosity here is the ratio between the applied shear stress and the shear strain rate. For a Newtonian fluid, this is constant. And with a constant viscosity, what this means is that the shear stress and the shear strain rate have a linear relationship as shown here. Now, there are also non-Newtonian fluids. This is not so common in silicate systems, but in many chalcogenide systems and also polymeric systems, also biological systems, there can be more complicated effects like alignment of molecules or maybe chemical reactions that take place in response to an applied stress that will change this relationship so it's no longer a linear relationship between shear stress and the shear strain rate. Non-Newtonian fluids come in different categories. One is a dilatant fluid. A dilatant fluid is one in which the apparent viscosity is increasing with the shear rate. So the faster that you shear it, or the faster that you apply the shear stress, the higher the amount of apparent viscosity that you observe. The classic example of this is a cornstarch and water mixture, where the faster that you shear it, the higher the apparent viscosity. The opposite of that is what's called pseudoplastic. In a pseudoplastic case, the apparent viscosity is decreasing with the strain rate. And the classic example of this is actually blood. So when your heart beats, this is increasing the amount of shear stress that actually causes alignment of the blood cells, which allows them to flow more easily through your arteries and veins. And so pseudoplastic involves a lowering of the apparent viscosity with shear rate. This is also known as shear thinning behavior. This is the opposite of dilatant, which is also called shear thickening behavior. So dilatant and shear thickening mean the same thing, and that's the opposite of pseudoplastic or shear thinning. Another example is a Bingham plastic. A Bingham plastic is a fluid that doesn't show any flow until the shear stress exceeds some critical threshold. So if the shear stress is below this yield threshold, no flow occurs. But once you're above that yield threshold, then then the liquid or the fluid will flow. An example of this is toothpaste. So if you've got toothpaste in a tube of toothpaste, you take the cap off and you just hang it upside down. The toothpaste is not going to flow. But if you squeeze the toothpaste, and you squeeze it enough that you go above this Bingham yield stress, then the toothpaste will start to flow out of the tube. Another special topic is volume viscosity. As I mentioned at the beginning, almost all the time when people discuss viscosity, what they actually mean is the shear viscosity of the system. The shear viscosity is in response to an applied shear stress or an applied biaxial stress, and what we measure is the shear strain rate. You can define a similar property with respect to hydrostatic or triaxial loading. In that case, we have an applied pressure on the system, and the deformation rate is not the shear deformation rate, but the volume deformation rate. And the constant of proportionality between those two is the volume viscosity, which can be denoted as an eta with a subscript V for volume viscosity. Now, this is a quantity that is very difficult to measure, and as a result, it's not measured very often, which means that there's very little literature on volume viscosity. So I'm just introducing this so you know that it exists. But from here on out, every time that we discuss viscosity, it is assumed that we mean shear viscosity. All right, next time we're going to get to different models to describe the temperature dependence of viscosity. But first, I want to introduce our glass great for this lecture, which is Ronald Walter Douglas. He lived from 1910 to 2000. He was the youngest of 8 children, and he grew up to become one of the most influential pioneers of modern glass technology in the United Kingdom. He was a researcher at General Electric, where he developed methods for measuring the viscosity of glass-forming liquids at high temperature that are still in use today. He later joined the faculty at Sheffield University in the UK, became a professor of glass technology there, and he was on the faculty at Sheffield for 2 decades. He ended up being one of the most influential figures in the Society of Glass Technology for over 40 years. So to summarize this lecture, viscosity defines the resistance of a liquid to flow, and it varies by many orders of magnitude as a function of temperature, also a function of composition. Different measurement techniques are required to measure viscosity in different regimes, and liquids can be classified as either strong or fragile liquids, depending upon whether they scale Arrheniusly or non-Arrheniusly with temperature. Next time, we will continue our exploration of Chapter 9 and dealing with liquid viscosity. All right, thanks everyone. I will see you then.